Hello, everyone. Now we're going to introduce the lecture 2 of our class. So in this class, we're going to introduce the Gauss law. So I believe everyone has learned the Gauss law in your, let's say, either sophomore or senior grade. But now we'll introduce it briefly in another way. So here in this textbook, it's just very briefly go through the Gauss law. If you want to review the Gauss law in details from the very beginning to see how to derive the Gauss law, why Gauss law is always true, the details are not included in this textbook. However, I have made another 2 videos which introduces the basics or origins of the Gauss law. I'll share the links at the end of this lecture so that you can go back to those videos to check how to derive the Gauss law, why Gauss law is always true. So we derived the Gauss law from Coulomb's equation to Gauss law in different formats. But here, let's spend a very short time to go through the Gauss law again. So first of all, from last lecture, we have introduced the equation 1.5, which is the integral format of the relationship between E and charge. So suppose the charge is not a point charge, then it might be a distribution of charge density. So rho is the charge density. And then by doing an integral, you will be able to calculate the total charge in, let's say, in a certain volume. And then this is the relationship between E and your charge. However, this equation is not always convenient for all situations. There is another integral result called Gauss law, which is more useful sometimes, and it can be easily lead to a differential equation of EX. So to obtain Gauss law, we first consider a point charge Q. Let's look at this figure on the top. We have a charge Q located here. And let's say we have a surface, a closed surface. And if we want to calculate the E or the electric field at certain point here, we can draw a line from Q to this point, and then we will know if there's only a 1 point charge here, then the direction of your electric field will be in this direction, from Q to this point. Let's say the distance between Q and this point that you concern is R. So that's the distance. And then if we define this enclosed surface, then at this point, there's a normal direction of the surface, which is perpendicular to the very small area of this surface. Let's define it to be N. So both N and E, they are vectors. Let's say they have an angle, which is theta between N and E. So once we define all of these, then we can describe this equation in another format or in Gauss law format. Okay, let's see. To obtain Gauss law, we first consider the point charge Q in the surface S, and then R is the distance between the charge and the point on the surface. N is the normal direction, and then dA is the infinity small element of the surface area. So in this case, dA is the area here. Let's say it's a very small. And then let's see, this is dA, and then if the electric field E at the point on the surface due to the charge Q makes angle theta with a unit normal, then the normal component of E could be written in this format. So E dot cross N times dA. So here's E, here's N, because there's a angle between N and E, so dot cross E and N, you will get, let's say, the once you dot E and N, then dot product E and N, then you got the component of E, which is along N direction, times N. But N here is a unit vector. So what you get is just the component of E, which is along N direction. And then if you do a dA, then what you get is Q over 4 pi epsilon cross theta R squared dA. Since E is directed along the line from the surface element to the charge Q, so cosine theta dA, which is here, equals R squared d omega. And there omega is defined as here. This is the solid angle of this area. So it can be written in this format, R squared d omega. And then this equation on the right could be written in this format, Q over 4 pi epsilon E, and then d omega. And then if we do integral, a surface integral, which is on the surface S, and then the equation could be written in this way. So on the left is the integral of your E. Actually, it's the integral of your E times, let's say, D surface. But the D surface has a direction, so it's a dot product between your E and dot surface, D surface. And then it equals to Q over epsilon if Q is inside S. Let's say in this case, if Q is inside S, then finally after the integral, you will have it equals to Q over epsilon 0. Otherwise, if your Q is outside this surface, then when you do a surface integral, in this case, let's say N and E, they're in similar directions, then the dot product of E and N should result in a positive number. And in this case, once E and N, they're in an angle which is greater than 90 degrees, it will result in a negative value. And of course, if N and E is in a 90-degree angle, it will result in 0. So summarize every dot product of E and N at all the surface areas, then what you have is 0. So if Q is outside S, then the integral equals to 0. This result is Gauss' law for a single point charge. If you have one point charge, either inside or outside the surface, this is the Gauss' law equation, the Gauss' law. For a discrete set of charges or multiple charges, multiple point charges actually, it is immediately apparent that this integral equals to the sum of multiple charges. And if it's not a point charge, if it's a charge distribution, let's say a continuous charge distribution, which can be described in a charge density rho x, then the Gauss law becomes, on the left, it's the same, but on the right, we will rewrite the sum into an integral. Similarly, it can be written into integral like that. So it's a density function times the d volume, and then an integral over the volume. So v is, let's say, where's my mouse? So here, v is a volume enclosed by S. So you just do the volume integral, then you get the net charge inside the volume. So this equation is one of the basic equations of electrostatics because it's considered as basic equations. So in this lecture, you can see we just spent a couple of minutes to go through it, but you really need to review it in details by using the videos at the end of this lecture. Please note that it depends upon the inverse square law of the force between charges, which is first introduced by the Coulomb's law. And the central nature of the force and the linear superposition of the effects of different charges. This is also introduced in our previous lectures. Once you have, let me see, where's my pen? Once you have one charge and you want to calculate the E here, then first of all, it's inverse the squared relationship between E and the distance. And then the central nature of the force. So it's always pointing from the center to this charge Q to this E in this direction. If the charge is positive, if negative, it's pointing in the opposite way. And the linear superposition means once you have multiple charges, let's say Q1, Q2, then Q2 generate E2, Q1 generate E1 based on the Coulomb's law, and then using the Coulomb's equation, you can calculate E1 and E2. Then you do a sum of E1 and E2. Of course, E1, E2, they're all vectors. When you do the sum, you have to use the vector sum, and then you will get the total E, which is shown here. So that's the three features of the Gauss law or Coulomb's law. Clearly, Gauss law holds for Newtonian gravitational force field, with matter density replacing charge density. So it's similar. The Gauss equation or Coulomb's equation is similar to the gravitational equation. Okay, so that's the introduction of Gauss law. And then let's see the differential form or format of Gauss law. So we have written it in, let's say, integral format. And here we can easily convert it into a differential format of Gauss law, just using some mathematics tricks. And it's simply from this equation, you can derive it in this way, and then here you can derive it from a surface integral to a volume integral, and finally you will get it for the differential form of Gauss law. So as I said at the beginning, this lecture is too brief. It doesn't provide details. For example, how to derive the Gauss law from the origin, step by step, and how to derive the integral function or integral format of the Gauss law to the differential format, step by step. It's simply too short. It doesn't have too much details. But fortunately, I have made 2 videos here and here using another textbook by David Griffiths. And then you can check these 2 videos. I also shared the slides for those 2 videos in Google Drive. You can check them out. And then once you check the 2 videos, then you will find more details, and you can come back to this lecture and go through it briefly again. You will see it's more like a brief review of Gauss law. Okay, thank you everyone. This is a lecture. This is the main lecture for today, and the main lecture leads to another 2, let's say, sub lectures. Make sure you go through all of those 3 lectures, the main lecture and those 2 detailed lectures, and check out all the slides in our Google Drive folder. Okay, thank you guys. I'll see you next time.